In the last video, we introduced the concept of the Metropolis-Hastings algorithm. Just as a quick review for context before our example, our goal is to generate samples from some really complicated distribution f. And the Metropolis-Hastings algorithm constructs a Markov chain in such a way that we're guaranteed that our samples will have stationary distribution that is the same as f, our target distribution. So our process for doing this was initialize our chain arbitrarily because our stationary distribution or target distribution does not depend on initial position. And then we'll generate a candidate y from some proposal distribution. Then we're going to have some mechanism for deciding whether we accept or reject that candidate. If we reject it, our next step in the chain means we're just staying in the same position or the same state. Our probability of acceptance was given by this function rho, the minimum between 1 and this ratio. We gave some intuition for that in the last video. Okay, so let's check out our first example here. Our target distribution is f given here. You'll notice the denominator is just the integral of the numerator over the space, so 0 to infinity. So this denominator is just our normalizing constant for the distribution. So not really important, it's just ensuring we integrate to 1. Okay, so for our Metropolis-Hastings algorithm, first we need a proposal distribution. This could be lots of things. I'm going to suggest we generate y given x, our current position in the chain, from an exponential distribution with parameter given by our current position in the chain. There's lots of options here. Two reasons for choosing this. One, it's easy to sample from. And then two, we need the space of our target distribution to be contained in the space of our proposal. So that's definitely the case here. I'll just say contains space of x. Or they share the same support, 0 to infinity. All right, so now down to our pseudocode. First step, we need to initialize, set our first time step to 1, and then initialize our first position or state anywhere from 0 to infinity. Doesn't matter. As we've said, the stationary distribution does not depend on initial position. Once we've initialized this, now it's time to generate our proposal. This proposal is coming from the distribution we chose. Again, this could have been lots of things, but let's roll with this. So our proposal distribution, q of y given our current position xt, that actual PDF here is 1 over xt. Now, this seems weird, but remember our parameter of the exponential distribution, we've defined it to be where we currently are. E to the negative y, that's our random variable, over xt, that's our parameter. Don't get confused there. Our next step is to figure out the acceptance or rejection of our proposed value y. So xt plus 1, the state we are going to move into next, will either be y, our proposed value, or the same place we already are. And again, that probability is according to rho. So here, rho, reminder of the definition, is the minimum of 1 in this ratio. So in our particular context here, this would be the minimum of 1. And f, this is our target distribution. I wrote it down here for reference. F is proportional to, and I just wrote the numerator. We don't need the normalizing constant because it's going to cancel out in this ratio. So here, just a reminder again of the kernel of the distribution, but I'm evaluating it at y, my proposed value. So this is y squared times absolute value of sine pi y e to the negative y cubed. And the denominator is the same thing but evaluated at our current position. We had that intuition earlier. We were kind of looking at this ratio of what is more likely, our current position versus the proposed position. And then the second piece here is our proposal distribution. So we jotted that down a moment ago. That was our exponential PDF. And so in the numerator, the variable is xt, the parameter is y. So let's jot that down. So 1 over, our parameter is y in this case, so 1 over y, e to the negative xt, our variable is xt, given our parameter y. And the denominator, that's just switched around, 1 over xt, e to the negative y over xt. All right, don't worry about how awful that looks. R will take care of it for us. All right, so we're going to accept or reject according to this probability, and then repeat again. Go back to 1 and generate our next time step. So let's check this out in R. So in R, you'll notice here we've got the first bit. We're going to just define that distribution for our target distribution as a function. I'll just call it f. And we've got our variable squared, absolute value of sine of the pi times the variable e to the negative variable to the third. So this is just defining f, so I don't have to keep typing it in over and over and keep things simple. All right, our function for the Metropolis-Hastings algorithm, I'm going to have two inputs. X naught is my initial position, so that's starting here. I can input a random starting position from 0 to infinity. And n, how long I want to run this chain. Usually this should be a pretty large number. We can talk about graphics in a minute to determine if our chain is converged or if we need to run it for longer. Okay, so our usual initializations, x, I'm going to store the outputs of my chain. So here x is my chain, resulting chain, the transitions from state to state that I'm making. And then the first position of that is going to be x naught, my inputted initial position. So the body of the algorithm is pretty straightforward. We're going to go from t from 1 to n minus 1. This indexing might seem a little bit weird. If you notice down here, I'm doing xt plus 1. So I've already got stored in slot 1. So next one will be stored in slot 2, t plus 1. And so I only need to go to n plus 1 because this will store it in spot n. All right, so first step, generate our candidate from the exponential distribution. And notice my parameter is based on where I currently am, so 1 over xt. Then row, let's define this ratio. So I've got my numerator here. And remember that had two parts. Our target distribution evaluated at our proposal. So I've defined the function f up here, so I'm just going to keep this a little bit clean, f of y. And then this was q of xt given y. So this was the exponential distribution, so I can do d, exp, and r to get the exponential distribution. My variable is the first input, so xt is my variable. My parameter is 1 over y. And then my denominator is the same thing, just switching the input, so f of xt. And then dxp, the exponential distribution evaluated at the variable y with parameter 1 over xt. So there's an expression for that ratio. Then I need to generate a random number to figure out if I'm going to accept or reject that proposed value. So uniform 0, 1 will be less than rho with probability rho. So if rho is bigger than 1, if this ratio, so that was the minimum of 1 and whatever this ratio is. So if this is 1, my uniform's guaranteed to be between 0 and 1 or less than 1. So I accept it, and my chain is updated. My next step was my proposed value. Otherwise, my chain in the next step just remains at the current position. And then I'm going to make sure to remember to return that vector storing all of my transitions to through the different states. Okay, so let's check out how to run this, the results when we do run this. So I'm going to run this for a bunch of steps, 75,000. I'll run this chain 4 different times with 4 different initial positions, a random uniform 0, 1. But again, this could be anywhere from 0 to infinity. So some random numbers in here, doesn't matter. Depending on what they are, it may or may not take longer to converge. So remember, the output of each of these is going to be my chain, my Markov chain that's converging to our stationary distribution or target distribution. So let's look at some plots to get information here. Remember, this little bit here, this is just optional. You don't need to store it somewhere if you don't want to. This gave us our 2x2 plotting window, so I can plot 4 things at once in the same window. So the first thing I'm going to plot is our density curve up to a constant. I'm going to ignore that initial position. And so I'm going to define my space from 0 to 2. I could, of course, this goes from 0 to infinity, so I could stretch it out more, but there's not much to see. And then I'm going to plot the x and then f. Let me make use of that distribution that I defined earlier, that function, f of x, and we'll see that plot in a moment. And then I'm going to just do a histogram of the samples from our previous chain. And I'm going to plot the first simulation, my first chain. So this is just as it transitions from step to step. I don't have an x and a y, so automatically x is going to be just time. And then the last bit here, I'm going to plot the convergence of the mean for all 4 chains. So even though they'll take different paths because I have different random steps being generated, hopefully they're going to converge around the same spot. So for each of these, notice the command here is the cumulative sum of our chain over 1 to n. So the first entry there would be the first state divided by 1. The second entry would be the sum of the first 2 states divided by 2. The third entry would be sum of the first 3 states divided by 3, and so on. So I get that cumulative sum. This part, don't worry about unless you opened like a PDF device or something to store it. Just ignore that bit. So let's check out the resulting plots for our example. So here's our first one, our density function up to a constant. Again, this could keep going if you want to peek at what it looks like out here. But we get a rough idea up to a constant of what our density function looks like that we should be sampling from. Here's a histogram of our sampled values. So it looks like we did a pretty good job sampling from this distribution. At the bottom, you see a realization of our first run of the chain. And this might look like a bunch of junk, and that's great. That's actually perfectly fine. So I ran 75,000 steps, and this should just be jumping all over the place, generating samples everywhere. And then finally, the convergence of the mean. You'll notice when we have few steps, our mean kind of jumps around, but eventually our chain is converging to that stationary distribution that the theorem gives us. So by this time, our 4 different chains have converged to represent samples from that stationary distribution or our target distribution. All right, next video, we'll check out one more example.